So we just talked about permutations, and as we said, for permutations, order is important. But suppose you're asked to find possible permutations of the letters A, B, and C. The total number of permutations for four letters would just be 4 factorial. However, they're not all distinguishable because there are two A's in this list. So like if I were to write the letters A, B, C, and I were to also write A, B, C, do those look any different? No, but I could claim that I switched the order of the A's. We'll never know. We can't distinguish them. So we're going to have to talk about this thing called distinguishable permutations. So to find the number of distinguishable permutations, we're going to use the following. So suppose we have n objects. So like say, for example, the four letters that we had up at the top here. And n sub 1 of one kind of object, so it's kind of like we'd have two ways of arranging the letter A, n sub 2 ways of the second object, n sub 3 ways of the third object, etc., etc., etc. So that way, when we add all those ways, we add up with the total number. But the number of distinguishable permutations of n objects is the total number of values, so n factorial, over n sub 1 factorial, the number of options for the first item, times n sub 2 factorial, times n sub 3 factorial, all the way until we end up with our final options. Now, folks, this I think becomes a little more clear once we start looking at our letters or looking at an example. It says how many distinguishable ways can the letters Mississippi be written? So taking a look at this, there's a lot of repeat letters. Let's just start with the first letter, the M. The M can happen just once. And we're going to call that our n sub 1. N sub 2 is the number of the ways that I happen. So there are 4 I's. So we'll say this happens 4 times. The next letter we see, we'll call that n sub 3, is the S. I'm trying to make it an exaggerated S so it's not confusing. That also happens 4 times. And then n sub 4, the last letter, the last unique letter would be the P, which happens 2 times. And then the total number of letters is just the good old n, no subscript, that's just 11. So following this formula, we're going to do 11 factorial over 1 factorial, the number of ways we can define the letter M, or arrange the number of letter M, times 4 factorial, times another 4 factorial, times 2 factorial. Now, the 1 factorial is just 1. I'm not going to bother writing that out. Let's cancel it out. 4 factorial, that's 4, 3, 2, 1. Well, there's a 4, 3, 2, 1 in the numerator, so I'm just going to write it out as 11 times 10 times 9, times 9 times 8 times 7 times 6 times 5. And again, we'd have a 4, a 3, and a 2, and a 1, but that would cancel out with the 4, the 3, and the 2, and the 1 that we had here. So let's just get rid of those now. So now we're just left with part of 11 factorial, because we got rid of the 4, 3, 2, 1 by getting rid of 4, 3, 2, and 1 in the denominator. We do still have that 4 factorial, so we still have 4 times 3 times 2 times 1. And then we also have this 2 factorial, so that's times 2 times 1. Now let's see if we can reduce this a little bit. Now, what I'm going to suggest is, well, we got some options here. 3 times 2. 3 times 2 is 6, so we can cancel out the 6 with that 6. Let's just do that. Bop, 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 gone. Also, we have a 4 and a 2. Well, 4 times 2 is 8, so let's cross off that 8 with this 4 and this 2. So now in our numerator, we're left with just 11 times 10 times 9 times 7. In our denominator, it's all 1, so it's just over 1. So we have 11 times 10 times 9 times 7. That gives us a grand total, you can type that into a calculator, of 34,650 distinguishable orders, or distinguishable permutations if you want. Because again, you can rearrange any of those S's and swap their places and you wouldn't be able to tell the difference. Now, when the order of elements is not important, that's what we call a combination. So for example, the combinations ABC and BAC are equal because they have the same 3 letters. The way I always describe it is like talking about if I were to invite friends to go to, well, the movies with me. If I call Billy, Frank, and Bob, it doesn't really make a difference whether I order Billy or whether I invite Billy first and then Frank and then Bob, or Frank, then Billy, then Bob. They won't care, assuming not, unless they're petty, but they shouldn't, because they're going to get to go to the movie with me anyways. And they get to spend time with me, which is the best prize that there is. But anyways, combinations, the order doesn't matter. The formula we're going to use for combinations looks really similar to what we had for permutations. So the number of combinations of n elements, so we choose from our large group of n, take an r at a time, so we're only choosing r elements, is NCR, so it looks pretty similar, just has a C instead of a P, equals n factorial over n minus r factorial times r factorial. That part is different. Now, it's different in that the only, like this part here, is the same as a permutation. So it's almost like you take the permutation and divide it by r factorial. Very, very similar to each other. Now, taking a look at this last example here, we're forming a 10-person committee from 9 women and 12 men. The committee must have 5 women and 5 men. Got to make it equal. So how many different combinations of this can we get? How many different 10-member committees? So for the women, there are 9 total women, and again, it doesn't matter what order they're chosen in. So we're going to do 5 and 9C5 for a combination. We'll do n factorial over 9 minus 5 factorial times 5 factorial. Cleaning that up a little bit, we got 9 factorial. 9 minus 5 is 4 factorial times 5 factorial. I'm going to cancel out the 5 factorial because 9 factorial is going to have 5, 4, 3, 2, 1. So in our numerator, it'll just be 9 times 8 times 7 times 6. All that divided by what we have left of 4 times 3 times 2 times 1. There's a lot of different ways you can simplify this. Let's see, what do I want to do? I'm going to do 4 times 2 to get rid of the 8. So we're going to get 4 times 2 to get rid of the 8 up top. I'm also going to take this 3 and this 6 and reduce it to 2. So now we have 9 times 7 times 2. That gives us 126 different women. So 126, and I'm going to say combinations or just combos of 5 women. So that's just the number of ways we can choose the women. Now the men, going to be a similar structure. This time we're choosing from 12 men, we're choosing 5 of them. So following the same pattern, we got 12 factorial, and I'm going to kind of skip part of this next part. We're going to have n minus r, in this case 12 minus 5 factorial, that's 7 factorial times 5 factorial. The nice thing is the numbers in your denominator, one of them, for combinations, one of them is always going to be that r factorial. The other one's going to be what you need to add to that to get to your n. So 7 and 5 add to 12. Now again, canceling as much out as we can so we don't have to write quite as much. 7 factorial is 7, 6, 5, 4, 3, 2, 1, which the numerator would also have. So we're just going to get 12 times 11 times 10 times 9 times 8. And again, we're canceling out the 7, 6, 5, 4, 3, 2, 1 because we canceled out that guy there. And that's divided by 5 times 4 times 3 times 2 times 1. Simplifying this a little bit. 5 and 2 gives us 10, so let's just cross that off with the 10 up top. 4 and 3 here adds or multiplies out to 12, so we can cancel out that 12. So now we're really just with 11 times 9 times 8, which is 792. And that's 792 combos of 5 men. So that's how many different choices we have for women, and that's how many different choices we have for men. Now the total number of 10-person committees is going to be, using the counting principle, the number of ways we can get 5 women, so that'd be 126, times the number of ways we can get 5 men, that'd be 792. When we multiply those together, we end up with 99,792. So there are almost 100,000 different ways we could choose 5 women and 5 men from those 9 women and 12 men.